So, welcome to Reccsar Private Limited, an esteemed IT training institute. We empower individuals and organizations in the tech era through diverse cut edge courses. So, and when it comes to our mission is to help organizations maintain agility in meeting evolving business demands. We build strong communities and bridge skill gaps between individuals and industries. So let's look into what we offer and what are our training modes. So we offer robust corporate training, blended learning, and custom solutions. Our training modes include classroom, online sessions, corporate and project-based trainings. And when it comes to the key benefits and the courses, the next slide, sir. Yes. So our training programs come with lifetime portal access, 24 into 7 support and industry experts. We offer courses in cloud and DevOps, web development and data and AI. So these are our courses. So please look into this one. You can even screenshot this. So these are our courses. We offer these courses in diverse colleges. So why choose Reza? So, because we are trusted global partners, industry aligned trainings, and personalized solutions. And the very important thing is proven outcomes in performance and efficiency. So, to reach us, you can contact. We displayed our contact information. You can just screenshot it if you want. So, you have the numbers and also the website details. So, please check it out.
So today we are going to see that online workshop of machine learning fundamentals from data to decisions. Now we will start the sessions.
So, good morning to one and all present here. So, I'm Neha Jacob, and I'll be giving you a small session on bias variance trade-off, overfitting and underfitting in machine learning model. So, basically, here it speaks about how a model fails, like why a model fails. That is what we are going to deal with today. So, here it will be like we are given a model and you are training the model over and over again to get a very good accuracy, very high accuracy of 99 percentage. But then there are chances that the model might not perform well in real life. Like a model can perform well with the training data you are training it with, but then later on when a new set of data, so so you are given with training data, and you are given with a model and you are given with a set of training data. And when the training data is provided and you're training the model over and over again, you will observe that the model gets trained well and it reaches up to an accuracy of 99 percentage. But later, when you're testing it with a new set of data, you will realize that when you're introduced with a new set of data, you will realize that the model is performing poorly, very poorly, up to 77 percentage, and most of the predictions are wrong as well. So, like, we'll go check out how check out the reason why the model is performing bad. So, initially, if you're given with a set of data points which are scattered all over, the set of data points which are scattered all over, and we try to fit. We are given with a linear model, and we are trying to fit the linear model to the data. We realize that most of the data points lays out, and it can't be fitted properly into the model. So under such cases, we'll have to use a better model, a better, more complex model. So like here, the training itself is not taking place properly. So testing will not definitely not take place properly. So here, what happens is the model is very simple to capture the complex properties of the model, and the model is way too simple. And if you use a polynomial kind of model which can fit larger amount of data points, it can capture more amount of patterns and analyze more about the data, and like make the predictions more accurate. So here the practical observations that we are seeing is, here we have a straight line and most of the data points are in non-linear format. Fitting non-linear data into a linear is not possible. So it could represent, like it could miss most of the patterns that are present. So the training accuracy as well as the testing accuracy will be high. It can't even predict properly how the training data works. So obviously the testing data will also fail. So this phenomenon is known as underfitting, where the model is too simple to learn the patterns present in the data. So let's look at an analogy example where everything is cold, where there is a doctor. Imagine there is a doctor who knows how to treat only common cold. He can't treat any other disease other than common cold. Like when a patient comes in with a broken leg, or when another patient comes in with an allergic reaction or a migraine, the doctor doesn't know how to treat them. So since the patients came, he's treating them with common cold, the medicines for common cold. It will obviously not work because every disease should be treated differently, and the doctor is not a general doctor can't treat every general diseases in this manner. So similarly, when you apply a nonlinear data, when you apply a nonlinear data and tries to fit it with a very simple model, as simple as a linear data, you will fail because the data points are complex, which contains more amount of patterns, and your model can't be that efficient to identify all the patterns. So this is like the model acts same as a doctor. The doctor can't send the patient away simply, so he'll prescribe some medicines. Similarly, your ML model will just do some prediction, give out the output, and doesn't care whether the output is perfect or not. It just gives out what it feels like giving. Similarly, like imagine a real life scenario where we are in a company and that company has a security section, and they decides or they validates if a password is proper or not, and they'll identify if the password is a strong password or a weak password. But in general scenarios, if we look at, like when we try to sign in through Google or something, we'll be asked to provide a stronger password where the length is of more than 12 characters or something, and it should contains numbers, characters, capital letters, small letters, special characters, and everything. But what if this company asks you to provide a character or a password of 8 characters long, and doesn't consider any of these criteria which a normal security sections considers, like for being a strong password itself, there are a certain set of criteria. But this company just focuses on getting 8 characters long. So a password as basic as password 123 will be considered as a strong password, whereas whereas whether the other strong passwords or the encrypted ones, which is 7 character long or 5 character long, will be considered as a weak password, which can't be even considered. And here, the model doesn't know what actually a password is, like how a password works, how well like what are the security criterions that people will consider, what are the weak passwords generally used. None of these patterns are taken into consideration. It just uses an if else condition and checks if the password is of 8 characters long or not, and then uses that for prediction purpose. So, like, imagine the extreme opposite scenario where you are given with the same set of data, which is very spread out, and you are asked to fit out. We are given any model possible, which is like we are asked to use any model for our purpose. So we'll obviously go with a more flexible model with higher polynomial degree. And what will come straightly to our mind? Like we'll think that we'll fit all the data points onto this line, so that like it will have a higher amount of accuracy, higher prediction rate, higher similarity rates, whatever it is. It will be like we'll just focus on the training data, and we'll try to fit all the points into the model very properly, very efficiently, getting 100% accuracy. Will that ever do? Will that be beneficial for us when a new set of models or when new set of data points are being introduced? I don't think so, because like when, okay, imagine a scenario where a student is mugging up all the data, like mugging up the whole textbook and going for exam. Will he be able to relate it to the outside scenarios, like outside scenarios, and apply it in an application level way? That might not be possible, like especially in mathematical problems where in textbook there might be a certain set of questions, like certain set of questions, and we'll be sitting and mugging up those questions, the answers, the final answers, including all the steps. But we might not be able to perform well in an exam because the values might be changed, the answers might be changed, everything might be like the question might be twisted, but the student might not be able to understand. Similarly, here also, when we are given with a set of data points in multiple, which is scattered, we increase the degree of polynomial to fit all the data points properly. Then, then also the model might not be accurate. We might think it is accurate, but it might not be accurate. So here, what happens is every data which is taken, it might not be perfect. It will have some random fluctuations, or certain random fluctuations might be present, or some noise might be, certain random noise might have been included, or calculation mistakes might be there. So similarly, nothing is perfect actually. None of the data are perfect. So there will be some noise that will be present in the data. So the model, if it is like having excess parameters or depth, the model will be trying to fit all the noises, all the valid data, everything into this model, making the model so complex and learning every pattern present in it in a by heart manner, and might not even generalize well. So the practical observation we are observing here is that complex curve patterns will be present. Like if you're using a complex curve, we'll try to fit all the data points into that curve. And this includes capturing noise, random fluctuations, everything and anything possible. So when a new set of unseen data is introduced into it, the model might not be able to generalize well and might not be able to understand the concepts properly and apply it properly. Just like a student going for a maths exam, learning his textbook by heart. So overfitting, so this process is known as overfitting, where the model learns the data very well, the model trains it very well, understands all the noise and everything very well, and then when it tries to generalize, it won't be able to generalize because it just mugged up the data. So, like, I'll explain it through a real life analogy example where, like, a student is given a set of previous year questions and set of formulas are provided to him or her, and that person is sitting and learning all the things that are provided to him or her in a by heart manner, thinking that all the values will also be same, all the things that are given to him will also be same. But then later, when the question paper comes, the professor slightly changed the values or twisted the question in a slightly different manner. So since that person didn't understand the concept, and he just memorized it, including all the formulas which he was unable to understand, he or she was unable to understand everything, he just mugged up and went, and doesn't know where to apply the formulas, where to apply it. So it's just that he or she won't be able to perform properly in such a manner. So like we all have our phones, right? If we try to open it using a face ID, our face is recognizable under most of the scenarios, despite the background, despite like despite whether we have specs or not. Similarly, the model is able to identify us, right? So that is also a practical example where the model is not too complex. The model didn't overfit. So obviously, it can't be a very simple model because facial recognition is something related to security, where when we try to log in and if it is not our face and if it opens up for somebody else's face, what is the security? What is the security? There is no security which will be provided. So under such cases, it is not a simple model. Now the extreme case that is possible is it might be a very complex model. So that is also not possible because imagine you're using a phone with which supports a very strict face ID, where you configured it sitting under yellow light, wearing glasses, postures and other things behind, in a very different setting, or sitting in your bedroom or whatever it is. The model will learn that image or that phase of yours very perfectly, that if such a scenario comes only, your phone will get unlocked. That is very bad, because the model, what the phone needs to do is just analyze our face and realize that it is us. And if such a model is overfitting, it won't be of any use. Such phase IDs won't be of any use. We'll have to carry our whole background outside to unlock our phone with our face ID. So this is a very big practical example for overfitting. So let's see what is overfitting and underfitting in a proper manner. So, like, if the model is very basic, very simple, it will be missing out on most of the patterns that are present and most of the things that are present. So, under such cases, the model misses out on a lot. And if such models might not be able to get a grasp of what the training data as well, so it will perform very poorly on the training data. And obviously, if a model performs very poorly on the training data, it will definitely perform very poorly on the testing data as well. So the training data, it performs very badly on the training as well as the testing data in case of underfitting. And it has a high bias and low variance, which we'll be exploring later. Similarly, in case of overfitting, the model condition is extremely opposite. Here, the model is very complex. There, it is too simple. So, since the model is very complex, it will have higher number of parameters. It will just focus on fitting the data very well, fitting the training data very well. So, fitting the training data very well implies that it will have a high, very excellent training accuracy. Like, it can go even up to 100%. The training accuracy can go up to 100%. Usually, when we initially started training a model, when we initially started with machine learning, we used to be very happy when our training model used to be 100%, where like we used to have various projects done, where the training process will be done with a data set which is taken from a random source. We don't know if the data set is perfect or not. It obviously won't be perfect. It will have its own problems. But then we'll be taking it, we'll be training the model, and we'll be getting, for especially for linear regression and other things, we'll be getting 100% decision tree and all without any parameters. Will be getting 100%, and we used to be excited. We used to be happy. But then, when a new set of data, that is a 20% of the testing data, when it was taken and when it was introduced to the same model, we realized that the accuracy fell short by 70% or something, whereas the training accuracy was really high. So when this was observed, we had to go back. We had to check what the issue was. We had to adjust various parameters that are present in the data, and we had to fit the data properly, and let the model not memorize the data, instead understand the data and learn the patterns. So the poor testing accuracy will be observed in case of overfitting, and low bias and high variance are also observed. So bias is basically models assumptions, where what is the error function, how much of the error, like predicted value minus actual value, what is the difference that is present, that is known as a bias. So like here, in case of if the training data is very proper, if the training data is fitted very if the training data is not fitted properly, then high bias is observed, there the data points, most of the data points lies outside the line. And what is the model actually learning? We'll try to adjust the line by adjusting the slope and the bias, but the model might not fit in a proper manner. So under such cases, the model doesn't understand the patterns at all, or doesn't even by heart the models properly. So the error that is seen, that is observed, will be very high. And since the error that is observed is very high, it will be it will have too many incorrect assumptions or anything during the learning process itself, and then it will spit out what it learned. And like when it is introduced with the testing data also, the accuracy will go down. So when there is high bias, underfitting, high bias leads to underfitting. High bias is basically a cause for underfitting. So variance. Variance describes the model sensitivity. What does variance generally mean? Like how much amount of fluctuations or something that is observed in a particular thing. So maybe the model is present and the model is trained with huge amount of data, and we are training the model such that the model gets trained very well to the data. This doesn't mean that the model is free of errors. It means that there will be small fluctuations that are present. So imagine an overfitted scenario where a model is provided with, we'll be having initially having a data set, and it will be split into 80 and 20. When it is split into 80 and 20, we'll be having the 80 percentage data, and that 80 percentage data is used for training the process, training the model, and that 80 percentage data fits very well into the model. But what if there is a scenario where you have to change that 80 percentage, where we have to shuffle the 80 percentage of data that is provided into the model? Will the model behave the same way, or will it behave a bit differently? Will it give the same accuracy or same things out? That is what we are checking here. So if a model is trained with one set of data, in okay, we can take two models. We can train one model with one set of data and other model with slightly mixed 80 percentage of data. Both the models will be different if it is overfitted, because in case of overfitting, the model just by hearts it, and the model will be very flexible that it will twist, turn, and the lines will be in a higher degree such that it will be twisted and turned to fit all the points. So here, higher variance implies too flexible data. The model is too flexible, and the data might contain noise as well, and it might learn all the noises also in a by heart manner. So if it learns all the noise as well, then it can lead to overfitting. So here we have complexity versus generalization, where the model complexity is plotted in the x-axis and the errors that are predicted in the y-axis. So here the model complexity is very low. Like the model is very simple, and as we move from the left side to right side, the model complexity increases. And let's focus on the training part now. So if the training error, this is a training line. The dark blue line is a training line, and here we are having a training error of 0.8 percentage when the model complexity is very less. And as we move down, as the model complexity slightly increases and comes into a medium range, we observe that almost 0.2 percentage is training accuracy. And later, if we move forward, we can observe that the training error is 0.05 percentage when the model accuracy, when the model is fitted very well, when the model is very proper, very complex. So similarly, if we check the testing error is 0.85, which is higher than the training error, which can happen when the model didn't even learn the training data properly. The testing as well goes like this. So the testing error is also high. And as we move down, we can see that the testing error is reducing as well as the training error is reducing. And when the model becomes a bit comes to a medium complexity, the testing error is very less. So the testing error is very less in the sense, so like model generalize well. And as we move further upwards, we can see that the testing error is going up, which is where the scenario where the overfitting takes place. So the left half, that is the low to medium region, is a region where underfitting took place, where the model complexity is less and the model didn't train on the data in a very proper manner. Whereas medium to high is a range where your model has overfitting, where the model learned a bit too much about bit lot about the model, about the data, and the model fitted the training data well. That is the reason why the training error is going further and further down, and it can even go up to zero. So that is being observed. So, whereas the testing error, after one particular point, it's going up because the model didn't learn about the testing error. Model learned all the noises that are present, and it deviated from the actual purpose. So that is happening here. So the main insight that we can get from this is that the model complexity, the model is very, if the model is very complex, then the model learns a bit too much about the data, and the bias, that is bias reduces. Okay, bias reduces, and the training error continuously improves. And when the training error continuously improves, the testing error also like the training error continuously improves, which means that the testing error also improves. And when the testing error improves, the testing as well as the training error is bad, and the model doesn't fit well. So this means that lack of generalization is seen. So, like, overall, we can understand that if the machine, in case of this machine learning, if the model is too simple, it leads to underfitting. And if the model is too complex, it leads to overfitting. And if the model is balanced, it generalizes well. And how can we balance is also a scenario. Here, the regularization is a process where which can be used for generalizing well by using various parameters. Like we can use various parameters and penalty scores, and adjusting the penalty scores and other things can help us in balancing the data. So we'll proceed with the demo. So, like, let's proceed with the demo. Here, I've taken the scenario of passwords. So here I've chosen the condition as if the password length is greater than 7, it will be like a strong password, and if the password length is less than 7 characters, it will like if it is greater than 7 characters, it will be a strong password, and if it is less than 7, it will be a weak password. So here I'm using NumPy as well. So here I've given a set of passwords that are taken into consideration. So here the passwords are mentioned, like hello one password, password 123, and all these passwords are being mentioned, and the length of password is being mentioned. And apart from the length of password, I'm also mentioning whether the password is actually a weak password or a strong password. So 0 means weak password and 1 means strong password. And the strong passwords and weak passwords are mentioned. And then we are going to analyze it. So we are going to iterate through all the passwords that are possible. And then we are going to consider PWD is a password. Here, this is a password. And then the length is being mentioned here. And then the actually, if it is strong password or weak password is mentioned, like it gets loaded into this particular value. And then we are going to iterate through all the passwords that are possible. Firstly, it goes to the pass one, which is this particular password. And then we are checking if the length is greater than 7 or not. Since the length is less than 7, it will not be a strong password. So obviously it will get a value 0, and then it will be mentioned as, if it is having a value 0, then it is mentioned as a weak password using the if else condition. And again, uh, we are taking the actual password, which is mentioned as weak or strong, which is actually given in the data. And if we are checking if it is 0 or 1. If it is 0, it is a strong password. If it is 0, it is a weak password. And if it is 1, it is a strong password. And then we are taking it. And since we are taking it and we are classifying it as strong password or weak password, here since it is 0 is given, it is a weak password. And then we are checking if it is a breach or not. It can be a breach when like the predicted string and actual string are not matching. Then it is a breach. So here the predicted and actual one is matching, like both are zeros. So since both are 0, it is considered as a weak password, and the breach is 0. It is not getting updated. But whereas if we consider if we can consider like the third one. Here the password is mentioned. It has a length of 8. And then when we go to this loop, we'll see if the length is greater than 7, it is considered as a strong password given a value of 1. So it will be given a value of 1. And then we are going to the predicted string, where if the predicted string is 1, then it is considered as a strong password. else it is weak password. So it is a strong password. Now the actual string. Here it is mentioned as a weak password because every like at least once in our life we would have thought a few we would have thought that we are forgetting the password very often and we have to remember the password just looking at it. So obviously the first password that comes to our mind is password 123, password at 123, or password $123, or something related to password. So since it is an easily identifiable password, it is considered as a weak password. So it is considered as weak, but whereas while considering the length, it is considered as a strong password. So there will be a mismatch. And if there is a mismatch, then since there is a mismatch, it is considered as a breach. And the breach value gets updated. And this continues for the whole set. And for in case of a for loop, it's running from top to bottom and then calculating the total number of breaches. And then the accuracy is getting calculated here. And after calculating the accuracy, we are doing the predictions. Like this is the final output that I'm getting. So here the password is present. The length of the password, since the length of the password is 4, it is considered as a weak password. Since it is actually a weak password as well, it is considered as a breach. Since the predicted and actual matches, it is not a breach. But similarly, hello, the length is 6. So it is a weak password predicted and it is a weak password in real life as well. So in A1 exclamation BC, this has a mix of characters. So it can obviously be considered as a strong password because someone who just thinks cannot directly crack it very easily. Similarly, all the two things that I mentioned here, both of them are considered a strong password. But the length of them, the only criteria that we are considering here is the length. So since length of it is less, we can't say that it is a weak password. It is predicted as a weak password. We can't say that it is a strong password, even though in real life it is a strong password. So since there is a deviation here, the breach it is marked as a breach. Similarly, here password and password 123, as I said before, it is obviously a weak password, which a person who doesn't want to forget the password will just put it to remember just by looking at it, just by looking at the password column. So mostly, obviously, everybody would have used it at least once. So it is definitely a weak password, which can be easily predicted. But whereas since considering the length, it is considered as a strong password. So the accuracy is 50 percentage. So obviously, the model is very underfitted. The model is too simple to understand what a password is and how a password will work. So it just considers the length and classifies it. So we can say that here the password might be long, but the password is weak. Here the password might be short, but it is strong. So it misses the important patterns, important characters that are present, and the complexity is also getting mixed. So let's consider a scenario. Let's consider another scenario. Here, I'm giving a set of grades like A grade or something like pass grades, good grades, bad grades, and all those. We'll be considering, right? So like if it is 90, it is a good grade. If it is 80, it is also a good grade. But then below 50 and all, it won't be considered as a good grade much. And we are giving the training data as well, which considers it as a pass or a fail. And then we are having a decision tree. Decision tree, obviously, everybody would have heard of what a tree is, where there are set of nodes and there are set of branches connecting to the nodes. And if we are not putting any limitation to the tree can fit this data in a very proper manner. The tree can fit the data in a very proper manner where all the data will be where the training data will fit it very properly such that we get 100% accuracy. So decision tree, in order to prevent overfitting, we have a certain set of criteria like maximum length can be if we check here, we can see the maximum depth can be present, the minimum number of splits can be present, minimum number of sample trees can be present. All these features are present. all these features are present, which helps us to understand, which prevents overfitting. And there are certain set of impurities or whatever that can be calculated to reduce the overfitting and like make it into a general model. But here I'm skipping every one of it, and I'm giving it as just a random state, and I'm going to fit the training data as well as testing data to it properly. And then after fitting the models properly, I'm going to start with the prediction. So here the training data is present, and then I'm going to train it. Now, like the predictions are done, and the accuracy, like how well the training data and testing data, like the training and testing worked, how well the predictions match. I'm going to find it out using accuracy score. And accuracy score can be like, it is also calculated from sklearn, which is a library. From there, it has some matrices. Matrices contain like evaluation matrices, like decisions, like F1 score, precision, recall, and everything. So I'm taking the accuracy score from there, and then I'm making the predictions, and then I'm going to convert it into percentage format, and then I'm going to display the results. So here I can observe that the training accuracy is 100%, whereas the testing accuracy is 0%, where the model failed very miserably. Um, Model failed very miserably because of overfitting, like how well the tree fitted the data. That is what is happening here. So whereas if we'll use the same decision tree, and we'll try to get better results with the same steps by adding a simple parameter called maximum depth. So here, we are still importing the tree from sklearn. Sklearn is as I said before, sklearn is a library, and from that it has a section called tree, and from that tree, I'm taking out the decision tree classifier. And then sklearn also has matrices, which contains evaluation matrices, various types of evaluation matrices. And there, the accuracy score is present. The accuracy score section is present, and then we are taking it as well. And then we are having the training data. We are having a set of the training data as well as the testing data is present. And we are trying to take the decision tree. We are going to apply maximum depth and the random state. Random state equal to 42. It's just a random number. Like when the shuffling takes place, it should take place in the same order every time you run. Like if I go with the fifth fifth data or fifth row first, every time I run the same code, the fifth row should be selected. That is the reason why the random state is selected like that. And decision tree classifier, I have applied maximum depth as 1, where the depth of the tree can go up to only 1 node. And then I'm going to fit the training data. I'm going to fit the data, and then I'm going to test it. I'm going to test it and make predictions based on the same data. And then the testing data is provided, and then based on the testing data, I'm going to make predictions, which gives the predictions are actually made by model.predict, where the predictions are made, and the accuracy score is used for checking out the accuracy. And like after that, everything is getting printed out, and the training accuracy is observed as 80%, whereas the testing accuracy is observed as 100%, which means that the model generalized well. And the model generalized well, and the model could understand the patterns present in the data, and the training accuracy as well as the testing accuracy went up to a proper limit. Here, the only difference that is observed is I just added a parameter here called maximum depth. Apart from maximum depth, the decision tree classifier also has various other things like minimum sample split, minimum sample leaves, and many other things. So that's all for the demo. And if you have any queries or something, we can go forward with it.